Hi, Peter.
Okay, hello.
There you go. I can hear you and I can see you. Great to have you here.
Excellent. Yeah, it's great to be here. I'll start sharing my slides. Okay, excellent. Thanks a lot, Lorenzo. Thanks also to the organizers for having me. It's an honor to be here. I think I wrote my first line of Crystal about 6 years ago in July 2015. So it's great after all these years to see Crystal reaching 1.0 and to have this conference with a way bigger community. So yeah, it's my pleasure to be here. So my name is Peter Schols. I work at Clinical Science and Interpretation Department at Invitae. Invitae is a human genome interpretation company. So they focused on genetic testing and providing answers for patients and their physicians. So let's first have a look at what we will cover today. We'll start by going a bit into genome analysis. What is it and why is it important? Then we'll cover Moon's architecture. Moon is a software that we built for genome interpretation. And last but not least, we'll discuss how Crystal helped us and what our advantages of Crystal are in this field, and also some disadvantages, of course, just to make it balanced. So first of all, I think I wouldn't be here without this person. This person is my father. And of course, that's quite obvious. No one would be here, I guess, without his father. But for this story, there is another reason, and that is that my father passed away after suffering from muscular dystrophy. And he never received a diagnosis before he died. And that's one of the reasons that encouraged me to start Diploid, which is a company focused on human genome interpretation and on providing answers for people with rare diseases. And it turns out, unfortunately, that my father was not alone. There's quite a bit of people suffering from rare diseases. If we look at the numbers worldwide, we see that worldwide 33 million people are suffering from cancer. 35 million people, unfortunately, are suffering from AIDS, but rare diseases, unlike what the name, what you would expect by their name, more than 350 million people are currently suffering from a rare disease. And again, they're rare individually, but there is over 6,000 rare diseases. So in aggregate, they affect way more patients than cancer and AIDS combined. And unfortunately, many of these patients are not a bit older, like my father. He started suffering at the age of 40, but many of them are children or even newborns, even babies. And it's striking to me because, oftentimes these rare diseases are extremely challenging for the patient, extremely severe, but on the other hand, they're also caused oftentimes by just one letter in the DNA, one spelling mistake in the human DNA that's incorrect, let's say. And looking at DNA, and this is a part of our human genome. This is part of our DNA that we all have. As you know, DNA consists of 4 bases, 4 letters, represented by 4 letters: A, C, G, and T. And here on this slide, we're looking at about 500 of these bases, as they call it. So to look at to review the whole human genome, it means that you would need to review more than 600 million slides or screens like this, which is of course a task that you cannot finish in your lifetime. And again, one letter, one spelling mistake in one of these 3.3 billion bases could be responsible for a very severe condition. For example, here you see that a T mutated in a G, and this could be a cause for disease. Again, finding this one letter is our mission, but it's also like finding a needle in a haystack. So we need tools, of course, we need software to help us find this. And one of the ways to reduce the amount of data is what's called a VCF format, stands for a variant call format. It's basically in programmer speak, I would say it's a diff. It's a diff between a patient's genome and a reference genome. And we know that the reference genome is not suffering from any major conditions. So we know that actually, basically, the one letter causing this disorder needs to be in the diff, and it needs to be part of what's different specifically for this specific patient. Now, this is already quite a help because we are reducing the 3.3 billion bases to a list of about 4.5 million variants. So on average, every person, if you diff your genome with the reference genome, you have about 4.5 million positions or 4.5 million letters, basically, where you are different from the reference genome. But that's still quite a lot. And to come back to our same slide with 500 base pairs, it would require you to still look at 9,000 slides like this to review all 4.5 million bases. Again, it's too much for a human. It would take you months to review all 9,000 slides. So again, people have found a solution by creating software. This is software we have created in 2014, but there is very similar software from other manufacturers. And it basically allows you on the left-hand side, you can see filters. It allows you to tweak these filters, frequency, gene association, and other criteria. And on the right-hand side, you see matching variants. And this way you can manually start filtering variants, manually start filtering mutations, and try to find the causal one. But this is still a very time-consuming process. It takes about 20 to 40 hours to find a causal variant like this. And it's time, that sometimes, it's not very urgent, but oftentimes, especially with children or newborns, there is a real urgency because they are admitted into neonatal intensive care, for example, and every hour can make a difference between life or death, because there might be therapies for the condition, or there might be ways to relieve symptoms a bit. And the more you know about the condition, of course, the more you can do from a therapeutic point of view. So that's why we designed our Moon software. We started working on it in 2016. It was released in summer 2017. And the aim is very simple. We want to reduce those 20 to 40 hours to just 5 minutes. Shortly after we released our software, we got a call from Rady Children's Hospital in San Diego. And they said, previously they set a Guinness World Record, and they told us, well, actually, we're going to shatter our own Guinness World Records. Would you like to work with us? And can we use Moon for this new Guinness World Record? And of course, we said yes, and they did so, and they were able to reduce the time from blood sample to diagnosis to just under 20 hours. Now, you might say 20 hours, didn't you mention 5 minutes? And indeed, our software takes 5 minutes, and that's for the final step of data interpretation. But of course, you first need to generate the data, which is actually done by sequencing a patient's blood cells, doing upstream bioinformatics, and then doing the interpretation using our software. So the entire pipeline, including wet lab work, takes less than 20 hours. These results have been published in Science Translational Medicine, which we were very happy about, as they show that our Moon software had 99% precision, and actually it was in some ways outperforming expert human geneticists, which is of course very important, not because it's a human versus machine race, but the better we can get, the better we can assist human experts in finding a patient's the cause for a patient's condition. Our Moon software was awarded by a Best of Show award at BioIT World in Boston, and also by an IVD label here in Europe. And it's currently in use in about 15 countries, going from Brazil to Germany, and from US to Japan, let's say. So it's widely used currently in hospitals worldwide. Now, I hope this sets the stage a bit, and this shows you a bit maybe what we're doing and why it makes a difference in patients' lives. Now, let's go into a bit more technical detail of how we are implementing this. And first of all, maybe a bit about the architecture. because that's quite relevant for today's crystal theme, let's say. And when talking about architecture, you often see the heated debate between the majestic monolith versus microservices. And in this case, we opted more for the monolith approach, not completely, as I will show, but this is for two reasons. First of all, until recently, I was the only developer working on the Moon codebase. And then, of course, from that point of view, it made a bit more sense to have a single code base, as there were no conflicts or there would be no parallel development anyway. But the more important reason is that microservices, where you have like services that offer an API and where data is sent over through a REST API as JSON, for example, all this is time consuming, especially given the amounts of data that we have to work with. In our field. So the performance for us, that was a huge reason. I mean, performance reasons were important in choosing more like a monolith approach versus microservices. Now, actually, we didn't really build a monolith. We built kind of a citadel approach. And for those of you that don't know the citadel pattern or architecture, it's been explained by DHH in last year in April. In which he says that the majestic monolith and the citadel keeps the majestic monolith at the center, but supports it with a set of outposts, each extracting a small subset of the application responsibilities. The outposts are there to allow the majestic monolith to offload a particular slice of divergent behavior, either for organizational or performance or implementation reasons. And that's exactly what we did, actually. And our reasons were mostly performance reasons. And that's exactly also where Crystal comes into play. So actually, we were using the Citadel pattern or architecture before it was published, because Moon was released in 2017, and this article dates from 2020. So it's a monolith app with outposts. And I'm going a bit more into detail into the architecture. We have two Ruby applications, the Moon core application that does basically all the analysis. So all the magic happens here. It's just a very simple Ruby application. A command line Ruby application. And then Moon UI, which actually displays and presents the results from the analysis that happens in Moon core. And Moon UI is a Rails application. But surrounding those two monoliths, so to speak, we have three Crystal applications. The most important one is the prepper application, which does a lot of the heavy lifting. So all the initial filtering happens in the prepper. So the prepper starts with the VCF file, again, remember, containing 4.5 million variants, and it reduces the amount of data by 90%. So it only sends about 10% of the variants, of the mutations, about 450K mutations to Moon core, so to the Ruby application. So in that way, we play, I think, into the strengths of each programming language, and Crystal is doing the heavy lifting, doing the major part of the data reduction, so that we can offer the Ruby side, let's say, with way less data, only 10% of the data. The same happens for Moon UI, where, of course, we need a kind of a QC for the VCF file that our customers upload. So when a hospital uploads the VCF file, the patient's genomic data, so to speak, the QC happens, and that QC happens in Crystal as well. Again, the good part is that we use Crystal on the full VCF file, because you cannot do a QC on, let's say, only 10% of the variants. You need to do it on the full genomic data. And Crystal can then offer to the Ruby application basically only a QC report, which is very lightweight. So again, two examples where we have Crystal outposts in our Citadel model that really take advantage of Crystal's performance. Another part, another outpost is the indexer that we have recently added to the Moon ecosystem, let's say, or to the Moon architecture. We're also using a couple of shards, not too many, from the Crystal community. One that I definitely want to mention is the RocksDB shard, a very excellent shard created by Maha to interact with RocksDB, which is a very fast key value store that we use pervasively in Moon development. We've also created our own shard, which is called VCF Tools, and it's a very simple library to work with VCF files in Crystal. It's open source, so if you ever want to do bioinformatics or anything in human genomics, you can, of course, you're very welcome to use it. And in development, not really in production, we've also been using ShyNet, which is a Crystal implementation of neural networks. Written by NeuroLegion, the guys I think that are currently giving a workshop in the 3rd track. So that's a bit about our architecture and the shards we're using. Let's go into the Crystal advantages. Let me check something here. Okay, so the Crystal advantages, we could just list them as bullet points, but I thought it would be more useful to discuss some of our team members and how they are using or how they are perceiving Crystal advantages and which Crystal advantage is useful to them. It's kind of think of it as a way to go through Crystal advantages through personas, so to speak. So we have 4 members of the team. There they are. Sander, Linde, Cyriel, and myself, and let's go through each one of them. Let's start with Sander. So he's a formally trained software engineer, and it's as many engineers, it's someone who loves perfection and who loves certainty and covering every possible scenario. Even though I'm sometimes saying, oh, but this is very unlikely to happen from a genetics point of view, Sander is someone who will sleep way better if he knows that even that branch, even that scenario has been covered. And for him, of course, and not just for him, but also for us, it's very important that Crystal is statically typed and it's a compiled language. As a compiler, we'll already do quite a bit in terms of checking and making sure, for example, that we don't run into specific errors that could be avoided at compile time. I think many of us have done some work in Rails, and we are still using Rails on a daily basis, and all of us probably had this error at some point, hopefully in development, sometimes in production. And it's so nice to know that with Crystal you will not have a null object exception, or at least that would be very hard. So knowing that a compiler is watching your back is so useful. Also, I mean, the fact that Crystal is statically typed, I've noticed now that the team is becoming bigger, it's so nice because you have to, I mean, you don't have to worry about documentation being up to date, and instead of specifying return types or argument types in docs, you can just have it as part of the method signature, which is way more consistent, and I mean, there is no, you cannot really forget to update the docs. That doesn't matter in Crystal, so that's really nice. Moving to Linde. Linde is a bioengineer, so she's basically a geneticist, but she has a huge interest in the software side of things, and she evolved into a bioinformatician. She put a lot of effort in self-teaching her how to program and how to write Ruby and Crystal code. Again, she has no formal software engineering background, but of course she's a domain expert in genetics. And I think it's very useful for those people to be able to contribute to a code base. And for her, of course, the key Crystal advantage is the fact that it's easy to learn and that she can even leverage her existing Ruby knowledge. When composing a slide to illustrate this point, I hope, I mean, it might be a bit controversial, but on the left-hand side, I have an implementation of a simple web server in Rust, and on the right-hand side of a simple web server in Crystal. And I'm not doing this to start a new language war or to say anything bad about Rust, but I think it definitely shows that if you're a domain expert and you just want to get work done in a programming language because patients are waiting for a diagnosis, I think it just shows that, I mean, your right-hand side has a learning curve that's way more friendly and way more approachable. And it's probably the language you would pick in this specific use case. And that's not to say, of course, that I mean, Rust has definitely its uses, and I could see for systems programming that you probably might want to go for Rust, but again, in our scenario, having the ability to use Crystal and not write slow code, for example, is definitely a plus. And I also think this is going to be more important in the future, because increasingly software is being written not only by engineers who had 5 years of training in all kinds of engineering practices and software development, but more and more by non-engineers, just by domain experts with low code, no code solutions. And recently, less than a month ago, Gartner published a report stating that the majority of technology and products and services will be built by professionals outside of IT in 2024. So by people actually who are not technology professionals. And I think that's very important. And I think this also explains the success of languages like Python and JavaScript, which are extremely approachable by beginners and by people that might not have this huge engineering background. So important. And definitely a plus for Crystal. Moving to our third team member, and that's Cyrielle. She used to be our CSO at Diploid, and she's still the scientific supervisor of what we do with Moon. She's also, just like Linde, she's a bioengineer, sorry. She's a geneticist. But unlike Linde, she's not really writing code. But of course, that doesn't mean that she's not reading code. And that's exactly what she likes to do when we make an implementation of a specific feature. She likes to dive into a specific commit or a specific clause, and she wants to make sure that it makes sense from a scientific point of view. And there also, again, the friendly syntax, the concise syntax, the very English-like syntax, the elegance of Ruby, let's say, is very important. For her, even if you don't contribute or write code. To illustrate this is an implementation of our allelic imbalance method. It's extremely simple. I think it's very easy to read for someone. I mean, as long as you know, what an if statement means and what a return statement means, as a scientist, you can read this code and you can make sure that it makes sense from a scientific point of view. And that's very important as well. Finally, for myself, I'm also not an engineer by training. I have a PhD in evolutionary biology, but I've been writing code for 20 years in several languages, ranging from Objective-C, JavaScript, Crystal, Ruby. But I do love speed and performance. And oftentimes in our field, you have to choose between like an easy solution using Python or Ruby and one that's fast. And the fact that there is no more balancing between Ruby's elegance or elegance of scripting languages and the speed of C and other languages that are maybe less approachable, that's definitely a plus for me as well. To illustrate the performance gain we're getting from Crystal, I want to show you benchmarks. Benchmarks for the QC application that I mentioned in the architecture overview. So this is for exome data. So this means all of a patient's genes. And a QC with time in milliseconds for Ruby takes 2,500 milliseconds, so 2.5 seconds. For Crystal, it takes only 540 milliseconds, so it's 4.6 times faster. And this is very cool in this case because it's a sub-second QC that can happen, and it means that our customers, when they upload a VCF file, they get, like, for them it's real-time QC basically. When they upload a VCF file and it's uploaded, the QC feels like an instant thing, which is great. For a whole genome, so for all of a patient's bases, the difference is even more striking. So Ruby takes about 170 seconds and Crystal only 27 seconds. So again, a huge gain of time, and also important because this makes a difference oftentimes between a geneticist having to context switch and do something else because he's not going to wait, or she's not going to wait for 170 seconds. But 27 seconds while probably looking or reviewing other results is definitely something you can still do, and it makes our customers way more productive. Again, this is a 6.3 times speed up thanks to Crystal. And we measured this by, I mean, we implemented this first in Crystal. We then ported it to Ruby, which is very simple, actually you're removing a couple of type annotations and you have the Ruby code. And we just did it for fun. We had no intentions of having this in Ruby at all. We just wanted to see, not in a micro benchmark or an artificial benchmark, but in a real world application setting, what the difference between Ruby and Crystal turns out to be. So to summarize, statically typed, compiled language, easy to learn, friendly syntax, and Crystal performance definitely make it a very good choice for us. Of course, it's not all roses. There are some disadvantages, but I think they are few and far between, and they're probably not really linked to the language itself, but more to the fact that the ecosystem is still very young. So the Shards ecosystem, it's great, there's already quite a bit out there, but of course, obviously, it's not as extensive as the Ruby gems ecosystem. So this applies to general purpose gems like Prawn, which we are using to generate PDFs from Ruby and Rails applications, but also for libraries and gems in bioinformatics, data science, and machine learning. And again, it's not like Ruby has such a huge repository of those gems. It's just that, for example, in Python, there is way more options. So we really hope and we contribute to Shards that can strengthen these fields within the Crystal ecosystem. But I want to end on a positive note, so I definitely want to point you to the ShyNet library from NeuroLegion. And I also want to mention that in the next few months, we're definitely going to announce more about this. And I think we're going to be able to reduce this disadvantage significantly. Thanks a lot for joining this talk and for attending. And of course, I would be very happy to answer any questions you might have.
Thank you, Peter. What a great talk. I can see there's a question from Kevin. We'll take just this one, and then I'm thinking, because the next talk is also around bioinformatics, maybe people have, the pleasure of actually speaking to you and to Leandro in the voice chat later on. So Kevin is asking how, if you have any thoughts on migrating the Rails stack to something like Lucky, so actually tackling the other two components of Moon.
Yeah, it's definitely something that's on our list, actually. So one of the things on our list is to migrate everything to Crystal, to be honest. I think the last thing to be migrated will be the Rails application, so the Moon UI application. Because there the performance is really, of least importance, let's say. But definitely the analysis application, so the Moon Core application it's on the list to be migrated to Crystal. I think there it's more like a business decision, since we're using Crystal already where it makes sense in terms of performance. The gain of porting the other applications to Crystal will not be the return on investment will be lower. So that's of course a business decision we have to make now with the people at Invitae, but it would definitely be cool to have like a full Crystal solution there, and it would definitely still offer an additional speed up. It will just not be as big anymore as it was with the Outpost applications that we created.
That's a very pragmatic answer, Peter. Thank you very much. We can also take another question. What are the main shards you would like to exist for data science and bioinformatics applications? I guess ShyNet is one of the examples that you mentioned. Anything that you feel is missing?
Yeah, I think some of the Python libraries for machine learning and like PyTorch, for example, would be very useful to see, or pandas, or I mean, similar charts like that would be very useful to see within the Crystal ecosystem.
And along the same lines, Francisco was asking how you address the lack of ML and data science tools for the Crystal ecosystem.
So there's still part of machine learning that's being done in a separate application that I didn't include for clarity into the overview of the architecture, and it's also actually a separate application which we call Apollo, and that's written in Django with a lot of Python machine learning libraries included. So there we've moved a lot of the ML that we are doing. Although again, we've also used the Shynet library and embedded it into Crystal solutions. Currently it's not in production, but more used for research projects surrounding our Moon software.
Thank you, Peter. And thanks to the audience for asking such interesting questions.